Hello, my name is Lilian Ibrahimi, and in this video I am going to present you the paper towards model reuse in local development platform based on knowledge graph, which is authored by me and by my colleague Dimitris Mozdelios. So we are both part of the CLMS company, which is known for its model-based engineering appliance. It started early in 1998 when the idea came how to bridge the gap between business and the software development part. So as there is always the need of understanding the right requirements from the one side and also understanding how to build the application from the other side, then how can we bridge this gap between business peoples and the software development team? Those CLMS thought how to integrate models or model-driven engineering in the software development part. So they created the low-code platform known as ZapDev, which they currently are supporting and creating softwares by using it. But what actually are low-code platforms? So there are many definitions related to low-code platforms. I have outlined here one of this provided on the paper from Apoorv and Sahai, which states that local platforms are typically cloud-based applications that serve for building full-stack software applications without necessarily requesting code knowledge. And there are a lot of evaluations of local platform foreseen, like the one in Gartner that says that on years so till 2024 local platforms will increase and they will be responsible for the creating of 65% of the applications. So it means that the majority of the software development process will be done through the low-code platforms, which means they actually have a very promising future. Nevertheless, even though the low-code platforms may be very demanded on the software development industry in the near future, they yet lack on some functionalities like pure scalability, fragmentation, pure software apps, etc. Those CLMS, as well as other industrial and partners from academia, they have created the project funded by European Union called Locomod, which aims to cope with this kind of issues currently presented in low-code platforms and raise the low-code platform into low-code engineering, in which is another level of low-code platforms without having this kind of current temporary issues. And creating the domain model of the target software under construction is the main task during coding, during developing on the low-code platform. So models are the core artifact on any low-code platform. But despite the growing need and importance of using models in low-code platform, there is yet limited support on discovering and reusing them, because there are different systems, similar systems like retail systems, shipping domain, banking domains, which in absence of any discovery and reuse mechanism will it comes to the need of a repetitive work and to always creating things from scratch, which of course can hamper both the productivity and feature completeness, but that leads to the necessity of having a model discovery and model reuse approach during performing the modeling task on a low-code platform. Before we think about a solution on how to reuse models on low-code platforms, how to discover, how to reuse their existing knowledge in order to construct new models, let's first discover the state-of-the-art approaches incorporated on some of the most used applications like Google, Facebook, YouTube, etc. If we check, for instance, Gmail, we have seen that when we just start typing some letters or a word, then we will get recommended a complete sentence, which is probably based on some AI and machine learning algorithms, which compares your words or typings based on some patterns and provides you recommendation systems here. Or for instance, Facebook, it provides you recommendations based on collaborative filtering here. So what kind of ads other friends from you have seen, liked, or so that may be also recommended to you. Or for instance, YouTube may recommend you relevant videos to you based on content-based filtering. So we see here that recommendation systems are very demanded and play the role of providing relevant artifacts based on reusing the knowledge from existing patterns, existing tasks, etc. And that can be, of course, incorporated also in low-code platforms. Hence, we aim to incorporate recommendation systems on low-code platform in order to reuse the existing knowledge for constructing new models. For instance, if we have a class trip and leg, which are constituting the model and the construction, or proposed model reuse, also model recommendation approach, should be able to get this information. So this class is trip leg, and by finding related models on the repository, it should be able to recommend relevant classes to them. For instance, it should be able to recommend a class like fair containing all its attributes, all the relationships to the related classes here, and it should be able to connect them then based on their relationships they have in the repository, like the photo, like the figure provided here in this slide. And before we go to the proposed approach, let's first introduce a bit the ZapDev models as a background information. So as said, ZapDev is a low-code platform which whose main artifacts are the domain models, also known as business objects. So the user working on the low-code platform, especially on ZapDev, they initially has to create the domain models, so the business objects, and on top of them is everything generated, also the user interface and so on. But the ZapDev domain models has also their own meta models, as seen in the left part on this figure here, which you see it has classes which may have also base classes. They have attributes, operations, associations, etc. And on the left part we have presented an excerpt of a business object model which is about trip, and you can see how it looks like on the ZapDev local platform here. As the first step towards model reuse, which is abstraction as described by Husserl et al., we selected to use RDF graphs, which are de facto the standard of the web, so standard of the World Wide Web Consortium since 2003, and which are originally designed as a data model for metadata and used for exchanging data across the web. And of course, since low-code platforms are mostly cloud-based, RDF seems to be a good fit for them. Then, as the query language, we have selected to use Sparkle, which is de facto the standard for RDF query language. So, the query language for querying RDF graphs. It is tailor-made for them. Then, Sparkle is a semantic query language for databases. It is a triple pattern-based language, so it uses the triple pattern subject, predicate, object in order to query. And finally, for providing recommendations from the next possible modeling step here, we have used n-grams. Of course, n-grams are continuous sequence of n items from a given sample of text or speech. In our case, we have classes instead of words, and we will provide based on class names instead of words or recommendations here. And here we go with our proposed approach. So we initially gather the information of different level agnostic and language agnostic models and transform them into an RDF graphs. So we are able to get information from any kind of graph-based models like XML, JSONs, RDF, Zebda models as introduced before, and so on. We used tailor-made parsers to transform all these different kind of models into RDF graphs, and afterwards all these RDF graphs will be merged into a single RDF graph, which will serve as a knowledge graph for our proposed approach. This graph will afterwards be weighted based on class term frequencies. For instance, if a class B occurs 5 times after a class A, then 5 will be given as the respective weight between A and B. And then the recommendation API, which will get the information from the information from the model under construction, so the class names, for instance, it will be able to query the repository by using Sparkle, and using n-gram, it will use n-gram to provide recommendation, which will rank-based recommendation, which will be given as a response to the user of any low-code platform here. So the way how it provides recommendations here is given in this slide here. So for instance, if we have a class trip and leg on the model under construction from which we trigger the recommendation service, this trip and leg will be given as an input for the approach here. So initially, our approach will use Sparkle to query the entire knowledge graph, so entire repository, to find this trip and leg pair. If it can find this, it initially localizes all the relevant models, which we call here domain-specific models here, and then check all the related classes to this pair trip leg here. For instance, we may have here fair type, point of interest, etc. here. If it cannot find any specific trip domain which has trip and leg, then it will check the entire repository to find the trip and leg pair, even though they may not be directly trip related, and get their related, so the pair related classes for providing recommendations. These related classes like fair type, point of interest will be afterwards ranked based on their term frequencies. Like here we see fair has an index of 5, which is above fair type, which has a lower index of 4 here, etc. Then fair type, point of interest, all this will be provided as recommendation to the user as related classes to trip and lag here. To prove the concept, we had to integrate Bora, so our model recommendation approach, into a low-code platform, which in our case was ZepDep. So initially we had to expose Bora as a REST API in order to be able to use it from any low-code platform. Then we hosted this REST API, so as a jar file containing also the repository in TDB, so the tailored made repository for our devs. We hosted all them in a Linux server, from which then we catched the endpoints from the ZepDev low-code platform in order to trigger the relevant recommendations and to use it to use it as a proof of concept in any real low-code platform here. And here you can see how Bora performs on the ZepDev low-code platform. So we started by creating the same model as provided on the motivation example here. So we created a trip and leg class with some attributes here. Then we selected both classes. So in case we select one class, we trigger a 1 gram recommendation approach. In case we select two classes, so then we trigger 2 grams, which means that the approach checks for related classes to this selected ones. In case we select 3 classes and trigger the get recommendation approach, then the approach checks for related classes with this 3 consecutive related classes here. In our case, we have 2 classes. We selected both in order to get all related classes to this pair, trip and leg. By pressing, of course, we trigger it by pressing the specific button on the menu bar provided here on the local platform. Then we got recommendations as seen here on B part, which we can see here we have fair and other classes. Here we can select one or multiple classes based on our choice. All these classes will then be, so all the selected classes will be integrated automatically on the modeling canvas together with their attributes, and they will be related to the classes they are related in the repository. For instance, fair is related to leg, thus it will be automatically related to leg here on the modeling canvas here. And in order to evaluate the performance of Bora, we posed these two research questions. So first we wanted to know how effective Bora is by recommending model classes during the model process of new models. So how active are all the domain specific and non-domain specific n-grams. And since we aim to build a reuse approach, the second research question is how effective is Bora by covering domain-related models classes from the repository. So the coverage. So of course the metrics, the relevant metrics, are the ones who are normally used by recommendation systems, which are precision, recall, the harmonic functional F measure. In our case it is F1, since we used the same weight for precision recall. We used MAP to measure the ranking process, since also Bora is a ranking based recommendation approach. And finally we use the coverage N in order to measure how many classes has been utilized, so discovered from the repository and utilized in order to provide modeling support for during the modeling process on the low-code platform here. And for the evaluation process, we used 667 different ZABDEV models in order to construct our knowledge graph. Then we selected 4 different models, of course not included in our repository, to simulate the recreation of these different models. So we tried to rebuild these 4 different models by using the support of the model recommendation approach. So we iterated through each class of these models under construction, so of these 4 different models, triggered the model recommendation approach and calculated the metrics. Finally, we provided in this table in the slide here the average of each metrics and also the standard deviation in order to see how it performs. And by looking the values, we can see here that Bora seems to be very promising on providing relevant model recommendations when it comes of reusing knowledge from different models from a given company here. As part of the evaluation process, we also devised a comparison between the domain-specific n-grams and non-domain specific n-grams, where shortly we can see that the precision provided on domain-specific n-grams is much higher than the non-domain specific ones, because of course they target first the relevant domains in order to provide recommendations, while the recall is higher on non-domain specific n-grams, because of course since in non-domain specific n-grams the entire repository will be checked in order to get something related to provide recommendations. We see also that the ranking is higher by 3 grams especially, which means of course when we have 3 consecutive classes, same as in the model under construction, also in the repository, then the ranking is higher because we will provide more relevant recommendations. Of course, for more details you can find them on the paper. So, to conclude, in this paper we have presented a model reuse and recommendation approach known as BORA, which stands for Business Object Reuse Approach, which persists different models on the F graph, and it uses that as its knowledge graph. It uses Sparkle to query the knowledge graph and use n-grams to provide recommendations. So Bora is available as a REST API and is currently integrated on the ZABDEV low-code platform here. Well, thank you very much for your attention, and I'm happy to answer any of your questions. Thank you.